Today we're going to start section 2, which has to do with reaction rates. We're going to begin studying how can we predict the rate of a chemical reaction based on the different factors we know that control chemical reactions. So to start this out, we're going to watch a video about lycopodium powder, and then we're going to ask some questions about what we observed, and that will lead us into the factors that influence reaction rates. Now you'll notice that the powder didn't automatically burn. In your book it talks about placing a jar of lycopodium powder over a flame, or in this video that we watched they put some lycopodium powder into a paper plate and aimed a lighter at it, and note it did not burn. But the powder did burst into flames when it was dispersed into the flames. And what explains the results? Well, from the video we learned a couple things. Is that in order for the lycopodium powder to burst into flames, it needed to have plenty of oxygen totally surrounding each of these lycopodium spores. So increasing the surface area was what we learned from this particular video. Now, so in this section we want to define chemical kinetics, and then we're going to explain two conditions necessary for chemical reactions to occur, and then we're going to discuss the factors that influence the rate of chemical reactions. We're also going to learn about what is a catalyst and discuss two different types of catalysts. And then we're going to figure out, when we look at a chemical reaction using the rate law, be able to describe what kind of order of reaction that is, which right now may not mean anything to you. And then we're going to explain and write rate laws for chemical reactions. So we're going to take some simple chemical reactions and write a law that describes how fast it reacts. The change in concentration of reactants per unit of time as a reaction proceeds is called the reaction rate. So how much of the reactants are being converted into products in a certain period of time. And this area of chemistry that is concerned with reaction rates and reaction mechanisms is called chemical kinetics. So that is a branch of chemistry. Now, several factors can influence the rate of a chemical reaction. For reactions other than simple decomposition to occur, particles must come in contact in a favorable orientation and with enough energy for activation. We already learned that in a previous part of the chapter. The rate of the reaction depends on the collision frequency, how often they collide, and on the collision efficiency. In other words, what percentage of the time are they colliding in the right orientation to each other so that the reaction can actually proceed. And the nature of the reactant, the surface area, the temperature, the concentration, and the presence of the catalyst are all factors that influence the rate of a chemical reaction. So let's begin with the nature of the reactants. The rate of a reaction depends on the particular reactants and the bonds that are involved. We could think about how fast, like for instance, iron rusts, as opposed to how fast iron particles in a hand warmer react. So there's differences there, and the difference in the rate of the reaction is not what particular reactions, but the surface area. And so the surface area shows us the difference. Now, in heterogeneous reactions, the reaction rate depends on the area of contact of the reaction substances. In other words, how much of the surfaces are they actually touching of each other. Heterogeneous reactions involve reactions that are in two different phases. Remember, homogeneous as if they were both in the same phase, like a gas reacting with another gas. This would be one where we maybe have a solid reacting with a liquid, would be maybe a possible example. And an increase in the surface area increases the rate of this heterogeneous reaction. The lycopodium powder in the gaseous atmosphere would be an example of a heterogeneous reaction. Now, temperature also influences the rate of a chemical reaction. An increase in temperature increases the average kinetic energy, in other words, how fast they're moving, of the particles in a substance, and this can result in a greater number of effective collisions. So we'll get maybe a larger number of these collisions in a given period of time, and then if we have more collisions, we can maybe then have more effective collisions. So if the number of effective collisions increases, then the reaction rate will increase. And at higher temperatures, more particles possess enough energy to form that activated complex. Remember, we needed to have a minimum amount of energy to form the activated complex, which we call the activation energy. And so at higher temperatures, there are going to be more particles that have that energy to be able to form that activated complex. So a rise in temperature produces an increase in collision energy, as well as a collision frequency. In other words, how often they collide. So they're going to collide with more energy, and they're going to collide more often. Now, concentration is another factor that influences the rate of chemical reaction. So a substance that oxidizes in air more vigorously if you put it into pure oxygen. So air is only about 20% oxygen, and then the other 80% is nitrogen. And so the concentration of oxygen in the air is only about 20%. But if I were to put this reactant that oxidizes in air into a pure oxygen environment, it would react much faster. So in homogeneous reaction systems, the reaction rate depends on the concentration of the reactants. You make them more concentrated and they will react faster, but because the particles will hit each other more often because there's more of them. So in general, an increase in rate is expected if the concentration of one or more of the reactants is increased. So if you increase one of them, you expect the reaction to take place faster. So if you just have, in this diagram in the upper left, it says one possible collision can occur between two reactants, between A and B. If I increase the number to 4, like I see in the upper right, I have 4 possible collisions that can occur in this system. If I go down to the bottom left, where I have 5 of them, I have 6 possible different collisions that could possibly occur. And then the one on the right, where we have 8 particles, we can have 16 possible collisions can occur. So as you can see, as we increase the number of particles, we're increasing the possible collisions that they could have. So the actual effect of concentration changes, the changes on the reaction rate must be determined experimentally. In other words, there's nothing that from the chemical formula and balanced equation that tells us the effect that increasing the concentration will have on it. So we have to determine that experimentally. Now, catalysts also can affect the rate of a chemical reaction. Now, sometimes their reaction rates can be increased dramatically by the presence of the catalyst. And what is a catalyst? A catalyst is just a substance that changes the rate of a chemical reaction without itself being permanently consumed. In other words, we don't use up a catalyst. After the chemical reaction is completed, the reaction will leave the catalyst there present and we can use it again. So the action of a catalyst is called catalysis. The reaction of a catalyst is called catalysis. A catalyst provides an alternate energy pathway or a reaction mechanism. So in the previous, when we looked at reaction mechanisms, we came up with an energy pathway that it would happen ordinarily without a catalyst. But if you bring a catalyst into the reaction, it may provide an alternate energy pathway or a reaction mechanism. In other words, a different kind of maybe complex formed. And this potential energy barrier between the reactants and products is actually going to be lowered. So quite often it requires less energy, activation energy, to get the whole thing started. So the catalyst may be effective in forming an alternate activated complex. And what that does is it requires less activation energy to make that happen. So it just makes it easier to start. We may not have to add as much energy, or there may already be enough energy present for the reaction to occur. Catalysts do not appear among the final products of the reaction they accelerate. So when we write out a balanced equation, we don't write it as one of the reactants. We often, if we're going to include it at all, we'll write the name of the catalyst over the arrow, but it's not part of the reactants, it's not part of the products. A catalyst that is the same phase as the reactants and the products is a homogeneous catalyst. So if the reactants and the products are both gases, then a homogeneous catalyst would have to be one that is also a gas. When its phase is different from the reactants, it's called a heterogeneous catalyst. So for instance, the exhaust in a car passes through a catalytic converter, and inside of the catalytic converter are solid metals that help the gases coming out of the car engine to continue to combust, and since the metals are solids, this would be a heterogeneous catalyst. So metals are typically used as heterogeneous catalysts. And that takes us to the end of today. Let's look at a graph of how a catalyst can affect the energies that are needed to get a reaction started. So we have here a reaction where it's a decomposition of hydrogen peroxide, regular hydrogen peroxide like you know about, and the red line at the top represents the energy pathway for decomposing hydrogen peroxide without using any catalyst. And it says that the activation energy is 75 kilojoules per mole. But in the purplish one that we have here, this one that goes over the hump right here, the activation energy is only 58 kilojoules per mole. So this is a catalyst that is also a liquid, and it is making it take place without requiring as much activation energy. It only needs 58 kilojoules per mole to activate the energy. The darker red one, the lower one right here, is where we're using an enzyme to cause hydrogen peroxide to decompose, and this one has a very low activation energy of only 4 kilojoules per mole. This would probably be one where just putting the liquid enzyme into the hydrogen peroxide would immediately cause it to decompose into hydrogen and oxygen, or oxygen and water. But then we have this one at the bottom here that has this kind of corkscrew looking thing here, and this is a heterogeneous process. These up here on the side were homogeneous. That means that the catalysts were in the same phase as hydrogen peroxide. It's a liquid, so they are also liquids. Down here, we're putting in a solid. Manganese dioxide is a black powdered solid, and when we dump it into the hydrogen peroxide, you'll notice that it immediately begins decomposing, and it follows an entirely different energy pathway than the other catalyst did. And so the activation energy is much lower than even the enzyme one. So, and the only way you can figure these things out is just by experimentation. So catalysts definitely increase the rate of a chemical reaction. Remember that they're still there at the end. You get to use them. They're not part of the reactants. They're not part of the products. And they provide alternate energy pathways or different ways of creating an activated complex. And they may not even be the same activated complex. They might be look differently, but at the end we still have the same products.